event is in the European time zone because we had so much response from people from other parts of the world, like Australia or Asia, Middle East. So we decided to shift that meeting to European time zone. So sorry for you guys in the US or in South America. But that, as Tegman already said, that event is recorded, so you can watch it later on the SPAA website, on the YouTube channel. So you'll get a chance to see it later on anyways. So welcome again. How does drilling mud affect our image is the title of our workshop. It's the third workshop that we organized of the borehole imaging special interest group from SPAA. And I'd like to welcome you on behalf of the board. My name is Christian Rambusek. I'm with Nymburk Geoscience. And the other members of the board are Bernd, you already know him, Bernd Ruehlicke from Eriksfiord. Peter Barrett already joined. He's going to give a talk together with Bernd. Peter's with Halliburton. Chandramani Srivastava. Did he join actually already? Or is he haven't seen him yet. With SLB, Tegman Perkins, you know him all. Active, and then we additionally invited two experts from the industry to join us for this event. It's Roberto Berto from ENI and Brice Fortier from Equinor. We're going to have four really interesting talks today, and I think I'll just hand over already to the first talk. It's held by Bernd Ruehlicke and Peter Barrett, you know them all, and the title is How Does Drilling Mud Affect Your Image? So I think we can start right into it. All right. Can you all see the slides, the screen?
Yeah. Yes, all good. Thanks.
All right, perfect. Well then, Peter, Bernd.
Thank you.
The floor is yours.
Okay. All right. We'll just do some introductions first. My name is Peter Barrett. I'm a borehole image champion at Halliburton for 1 year. Been working with images for 30 years, and I'm pleased to have two experts with me here. Eric van Beest. Bernd, do you want to introduce yourself quickly?
Yep, I'm. Oh, sorry.
Yeah, go ahead, Bernd.
Okay, I'm Bernd Ruehlicke from Eriksfiord, and I think I have been as with images as long as Peter, back from 1992 in Stavanger with Petrobank and the ZNS Group and the Halliburton Landmark, PGS Data Management, and Eriksfiord now.
Okay, my name is Eric van Beest. I'm a global technical advisor with the Bayreuth product service line of Halliburton. My specialty is lost circulation materials, wellbore strengthening, and wellbore stability. I haven't been as long as images as any of you guys, probably the shortest of all, even though I've been with Halliburton this year for 30 years.
Thank you, Eric. So the agenda very briefly is what is drilling mud? Then we look at some acoustic image artifacts, some artifacts on resistivity images, including newer images and older images, because due to different technologies, we have different kinds of artifacts. Then we're going to look at some interpretation considerations. But first, Eric is going to give us an overview on drilling mud.
So okay. Who's running the presentation? Yeah, who's forwarding the presentation?
Yeah, I'll run the presentation.
Okay, cool.
Okay, go ahead. Next slide then, Peter.
Do you not see it? It should be there, Eric.
I'm on the agenda slide.
Has everyone else just seen the agenda?
It's the agenda.
Just the agenda.
Agenda, yes.
Sometimes Teams is a bit slow. Try going back and then forward again.
Do you want it?
There we go.
Nope.
Okay, drilling mud.
Yeah.
Most of you will be familiar with that brown stuff that's circulated around the wellbore. What is drilling mud? Drilling mud is the fluid that's used to control that wellbore. Amongst its most important functions is cleaning out the drilled material from the wellbore, controlling the subsurface pressure so we don't get a blowout, lubricating the drill string against the rock so we reduce the amount of friction and transfer more power to the bit, and indeed driving downhole tools such as MWDs, rotary steerable tools and such. That quite apart from the functioning as a conduit for wellbore logging tools, because logging in an empty hole is not so easy. Very broadly for us, in this discussion, there's two categories of drilling mud. There's the water-based fluids, where water or brine is the continuous phase, and oil-based muds, where oil or any non-polar solvent, where that is the continuous phase. In the latter, the water or brine is emulsified into the oil phase, so it makes up the discontinuous phase. And for this reason, we call it invert emulsions, just to distinguish them from regular emulsions that have oil inside that water phase. In both cases, though, solids are also a discontinuous phase. We may further separate water-based and oil-based muds into old-style clay-based fluids and the more modern high-performance ones, which are largely polymer-based and where there's much stricter control of quality and solids content, just to speed up the drilling process. Next slide, please, Peter. It's a come.
Okay, I'm there. Do you see it?
Not yet. No.
Yeah,
Not
there
yet.
we go.
But what sets these categories even further apart, or the broad categories, oil-based mud versus water-based mud, is how they render their filter cakes. And it's also something that is an understanding that is not, I'd say, even well known within drilling mud circles. Water-based mud, mostly it is water with solids, sometimes emulsified oil. And what you get in the filter cake is mostly the solids, and that don't go into the formation, and whatever water is not squeezed out of that void space from that filter cake. So a lot of the filtrate is the brine, and the filter cake is mostly solids with a bit of water in between. Oil-based mud, weirdly, generates a filter cake which is mostly the emulsified water. In most cases, the brine phase makes up more than the oil phase. Both are discontinuous. So what gets left behind in that filter cake is largely the brine or the water phase from the oil-based mud. There's the solids too. Those also don't travel into the formation. And the continuous phase, even in an oil-based mud filter cake, remains the oil. So everything gets coated with a nice layer of oil. So strangely enough, your oil-based mud filter cake contains this vast amounts of conductive phase, the brine, which acts as a conduit for all kinds of weirdness that you would otherwise not see in a regular oil-based mud. Now, filter cakes, or at least filter cakes from LCM bills, they usually have a greater solids content, so maybe more conductive also than the oil-based mud that they were transported in. Back to you, Peter.
Okay, thanks, Eric. Has the next slide shown up?
Not yet, Peter. It takes a while, I guess. Long line. There we go.
Okay. So the first of the image artifacts is one that we see fairly commonly on acoustic images, and this is a fairly simple one. But when we do have mud cake form, and we run several tools in the hole, such as density tools with their pads which are pressed tight against the borehole wall, the various centralizers used to centralize the tool, they often tend to form these vertical lines which we see in the wellbore, just as vertical cases. And again, we can see at the top of the image here, around about 1762, that we do have some features here, but they're obscured by the centralizer traces which are running vertically through the wellbore. Another situation that we tend to get with acoustic images that we've been seeing for many years is the wood grain effect.
Takes a while, I guess.
The wood grain effect, is it there?
Nope. Interesting.
I apologize for the fact that it's taking a while for things to update from my computer to what you're actually seeing. But I think several of you are probably familiar with the wood grain effect. This is where we see a pattern on the acoustic images that is similar to the grain that we see in wood. And when you see this on an acoustic image, if you look at it, you'll see it occur in more permeable parts of the formation, because again, it's the mud cake that is causing us to see this wood grain effect, and it can be enhanced further if the tool is slightly decentralized. That hopefully you can see here is a more extreme example of where we have
not yet, Peter. It's
sorry?
still the stripy image.
Oh, do you want to take over the display of the slides?
Maybe I can try from my side if I have the rights to share. Can I share? Can I try?
Yep.
Let me try to share this on my screen then here. This might help. Sorry about that. Slideshow. Okay, run this guy there. So how does it look with you guys? Is it better from here?
We can see it now.
Yeah, that's good.
Let's go forwards once and back.
Hmm?
Let's go quickly
where
forward.
we need to be.
There we go. Perfect. Okay, good.
And now I go back to the wood grain.
Yeah.
Okay. Cool. Peter, are you still talking that wood grain, or should I take the next?
Yeah, so I was just saying the example that we can see here is a very extreme example of wood grain. We'll still see some information we're seeing here, but it's very much obscured by the wood grain, and wood grain is something that it's not easy for us to filter out. Many of the artifacts that we do see, we can actually improve through filtering. We always stuck with to explain in the next slide.
Okay, I can try the next slide. That is another example of a more peaceful.
Next slide, Bernd.
Yeah, this is a more example of a more peaceful wood grain. I hope you can see this image. This is two images. On the left and on the right is the same data, and on the left side it is the standard amplitude deliverables of these wireline images, whereas some tools have the option to get the first echo, what is called like that is the first response, and in this case it is reducing the effect of the wood grain, as you can see on the right image. So there are different image arrays available, not always loaded by default or recognized by different softwares, but different vendors have these different arrays possibly available. So it's sometimes worth take a look at that. So on the next slide is also an example of an extreme wood grain. In this case, we're talking a dual physics tool, which can save the day. Very often, in particular the newer dual physics tools, LWD tools, we have had quite a success with those images when one of them is giving up, the other one is saving the day, as we can see in this example, where the ultrasonic to the right is really suffering greatly, whereas the resistivity images on the left are not inside the same situation. So this is a good example where dual images is coming in very handy. There are other intervals where it's the opposite, where the resistivity image is failing and the ultrasonic is good. So Peter, I think you can take over this one.
Okay, yes. So this is just an example of one of the new oil-based mud imaging tools that is out there from the various service companies. These run at various different frequencies. They have a lower frequency and sometimes a middle frequency and a higher frequency, sometimes two, sometimes three frequencies. the lower frequencies work better in high resistivities, and the high frequencies work better in lower resistivities. But the problem with the lower frequencies is they're more affected by standoff at low resistivities. As we can see here, that the black line is showing with just 4 millimeters of standoff, we've lost all the dynamic range in the signal. The higher frequencies have the problem that they're affected by permittivity effects. Permittivity is a measure of capacitance. And in this example here from around about 20 ohm meters, it's actually starting to roll over. And then as the resistivity of the formation increases, the response decreases. But these tools have their own particular responses that we're going to look at in oil-based mud. Next slide, please, Bernd.
Just a second. Down.
So what we actually record with these tools are the phase and the magnitude of the response, because it's actually an AC signal. So, if we're running 2 frequencies, we have 2 phases, 2 amplitudes. If we're running 3 frequencies, and we have 3 of each. What we typically tend to generate is what we called an impedivity image. An impedivity image, we deal with them like complex numbers, is the real part. So it's the magnitude multiplied by the cosine of the the cosine of phase. And this image is dominated by formation resistivity. We can also generate an imaginary part, which is dominated by the phase, and the phase in turn is dominated by the permittivity of the formation. So let's look at the next slide, Bernd.
Can you see it already?
Yeah, Bernd, next slide.
Yeah, can you see it already? It's on there. Maybe it's delay for you.
I'm not seeing it. It should be the
3 images.
The fractures in oil-based mud.
It's there. It's there.
You have a slow line, Peter. Maybe it comes in a second.
All right, I apologize if you can hear me okay. So what we're looking at here is an example of the real and imaginary data. The real is in the earth tones, and the imaginary data, which is dominated by permittivity, is in the grayscale. And what we see here is a fracture. The response on the real image is that it looks like a conductive feature, whereas on the permittivity image, we see that it's very bright indeed, and very bright suggests high permittivity. High permittivity is a response to water, and this goes back to what Eric was talking about earlier. So what we're actually seeing here on the permittivity image is the response of the mud cake, and the brine that is in the mud cake is now within the fracture. The mud cake is in the fracture. So we're seeing this high response on the permittivity image, and we've got the conductive response on the resistivity image. So when we see a response like this is probably a mineralized fracture, but using the extra information that we've got from the permittivity image, we can actually deduce that this is probably an open fracture. And if we take it a stage further and look at doing an inversion on this data, next slide, please, Bernd.
Yep, I switched already.
Okay, then using the different frequencies, the fact that the frequencies respond differently to standoff, as we saw on the graph earlier, we can generate a standoff image. So the standoff image is a bit like a travel time image from an acoustic tool. And here we see the same fracture again. We see that it's got a longer response, if you like, on the standoff image, suggesting that this fracture is indeed open, and that using the resistivity and the permittivity images alone leads us to that response, but having the inversion results here just proves what we're saying. And pretty typically, the different service companies will deliver to you either real imaginary data or the phase and amplitude data. If you look at both of those, the amplitude will be very similar to what we see in the earth tones here. The phase will be very similar to what we see in the grayscale here. Using both of those together will help you with your interpretation to get the best out of this data. Okay, next slide, Bernd.
Yep, that is me then. So these are other effects we have seen on the newer tools on the market. We have seen in old days from the water-based initial image logs coming out in the 90s that that mud cake is present in water-based mud, and very often image quality is degrading over where we have mud cake. But we can also confirm this now on the newer images on the oil-based mud, that mud cake is present and mud cake has an influence on the image. This is one example where we call it the see-through or the Scooby-Doo effect, like, you know, like a rubber mask you're dragging off. And you can see that on the left we have a static image, on the right we have a dynamic image. And you can see that some of the pads are influenced by a mud cake buildup, and you can still somehow look through this kind of build-up and follow these the true formation dips going through where they're a little bit broken up, like a rubber face Scooby-Doo effect. And the next page is another example of that. I hope you can see that as well. This is exactly the same effect where we can see at depth 8x8, we can see a chunk of something which you would not know exactly what might be, but this is actually a mud cake. And you can, if you look, I hope the image is very good, and you can see that this formation can be looked through the image. You can see it here coming through as well as here. And in addition, these modern tools have individual radii for each arm, and indeed exactly at this depth, the readings of this pad is smaller. So this is very much a proof of mud cake and an image, an oil-based mud image of a mud cake, which is for me a super cool example. And it stops discussion. I think in old days the discussion were that oil-based mud doesn't have a mud cake. I think this should settle that discussion. This is of course open for, we are all together for this. We just show these examples and we can always discuss that later. But I think this is a very, very good example of this. There are other examples we want to show and share with you that these modern tools can read when the pads are closed, and I keep this for open for discussion. You don't have to argument on this now. We can have that maybe later, but I just want to share some examples. In this example on the left, we have one of those more modern oil-based mud tools where the pads were open as they should be, and on the right, they were closed and locking through. You can see that the pads in this case are drawn wider. That's because the pads are closed and it's the same width, but you can see the same geological feature can be detected. And it's very interesting that in this case, the resistivity of the rock was actually quite low. And for me, it was quite surprising that this worked at all, because just following the physics of the tool, it should not really read rock at this time. But it does. And there's another example on the next page, very similar. On the right this time, we have the tool coming up as it should do with a normal pad wall contact. The image was shifted a bit just that we can pick the same feature on one of the image on the right, and we can also pick it on the left when we just increase, make a depth on investigation, which is the real depth on investigation plus the distance from the closed pad to the wall, to make a kind of fake depth on investigation, and you will get similar dips coming out. So it's kind of a poor man's, well, nearly better than LWD image, I would say. So it's not lost, and I'm still surprised why it works, and I've seen it numerous times now on numerous different tools. So if you had that situation, don't make the tool lost. You can still work on this and get information out of that. Peter, over to you with the desiccation 1 slide.
Right. So something that we've seen for many years on the older generation of oil-based mud images are shown on the 2 tracks on the far right here. And these are desiccation tracks. And these are developed due to subaqueous shrinkage of muddy sediment, which is caused by differences in salinity or chemical conditions. We look at the same set of data here. On the right, we see the older style of oil-based mud imager, and on the left, we see the new style of oil-based mud imager. And we can see the difference here and the effect that the desiccation cracks has actually on the image itself and actually on the image interpretation. It's very easy to join up these desiccation cracks and make artificial features out of them because they can appear to be continuous or discontinuous. And again, they come and go with formation changes. I think all of us that have been dealing with these images have been seeing them for years, but when you see the difference between the two images here, it's really stark, the effect that they can have on image interpretation if you do not know what you're looking at. And the next slide, please, Bernd.
Yeah, that is coming up now.
Okay.
It is there now.
Yeah. So here there is observed over a more muddy interval, as you can see, as well as across an entire interval with changing lithology. So it is really neat the way you can see here how they change with the lithology in the middle here, around, well, as Bernd is showing with his pointer here. But again, it's something to remember when you do see these. It's not a whole load of open fractures. It's desiccation cracks, and they only affect the older style of oil-based mud images. Bernd.
Yep. So just 2 more slides for this. The interesting part is also that, of course, when we have images, we can't resist running them, even in environments where they technically shouldn't run that, and the engineers will most likely kill us all doing this. But this is an example where we have seen also in other situations that if you have a high resistive rock, it is possible sometimes to run a water-based conventional tool in an oil-based mud. And this is an example where it shows the linkage between a higher resistivity rock, which is seen on this little red curve here, a high resistivity in the upper part, and a lower resistive rock in the lower part. And the image turned out to become very good in the high resistive rock and not very good or very poor in the lower one, as expected, because the tool is not designed for this kind of environment. There is also an example where we have, in this case, a classic oil-based mud to the left tool. So these are 3 different images shown here, run over the same interval. So this is the classic 2000 model oil-based mud imager. And in the middle, we have a water-based mud imager run in the oil-based mud. And then on the right, we have a classic acoustic tool. And shown here, it is a high resistive rock, and it seems to work very well. And we also can confirm that this tool is literally run in oil-based mud by this feature, a dark feature on the amplitude is an open feature, and it comes out bright on the quotation mark water-based tool. And since this is oil-based mud, it comes correctly out in the white color. The older fashioned oil-based mud tool doesn't recognize this feature at all. It's totally blind to this feature. Other features you can see come very strong out, like these very thin fractures, which are open fractures. They come out very strong on the old-fashioned oil-based mud tool. You can also see this guy coming in here. This open feature here comes out quite nice, strong on the old oil-based mud imager. So I thought that's quite an example you don't see every day, where you have 3 different images run over the same interval in oil-based mud, where you run a water-based tool as well. And this is happening quite frequently, and it works sometimes. So the final result is in consideration and interpretation, which we can share here with the team, is that know the difference between what we call old OBMI tools and the newer generation. And what I mean with this is the tools which came around year 2000 and the tools which came around, correct me if I'm wrong, it's around 2015 in this area, plus minus a year or so. They are fundamentally different. We used to know the physics of these tools. The initial oil-based mud tools use more or less Ohm's law, whereas the other one treat the mud as a capacitor and use high frequency beams in different frequencies to penetrate the effect of the oil-based mud. The older tools have, as Peter was showing, desiccation cracks as one of their artifacts which they pick up, which the newer tools do not see. And they also have something called shoulder effects because of the design of the older tools with the two plates and the currency coming out. And the reason I write this called a longitudinal probe, you might know these tools. They have these big pads, huge pads. That's why they also have these shoulder effects. And the probe or the currency goes along the tool, which I call a longitudinal probe. And that's why you will very often not be able to see fractures or, let's say, high apparent steep dips, where the newer tools have a radial probe going straight out, and they can detect those things. That's why we also, what Peter was showing was that the desiccation cracks were totally gone on the newer tools. So the newer tools also have their artifacts. Nothing is for free in this world. The classic rollover effect, which Peter was showing, if you have one of the frequency or all of the frequencies start rolling over if you get further and further out, meaning that the tool gets seeing the opposite direction than the actual rock of the tool, the actual resistivity of the rock. And then we also have more frequencies. We have more data. We have phase versus real versus imaginaire versus magnitude versus composite. Blended are the words used, where different suppliers use the different frequency and blend them together. If you have a variation of not just low resistivity rock or high resistivity rock, but you go through a change of high to low resistivity rock, like this one example I showed. And the depth and investigation is different of these tools. The newer tools have a much smaller DOI than the older tools. And we also have to be careful with the newer tools have more pads at more different depth levels, and processing will occur at different depth levels, and we have to be careful that this matching is all working. So the newer tools are a little bit more complex, but for sure the results are astonishing from what we have seen so far. That should be it from here. No, how we take it from there?
Well, I think Baker released their dual frequency tool in around about 2010, Schlumberger 2014, Halliburton around about 2018.
Mm-hmm. And when did the original Earth imager come out? I think they already did that in 2002, right?
Correct, yes.
Yes.
That
so
was
that
a
was
single
the initial
frequency tool.
Yes, that was the initial idea with the capacitor and this single frequency. Mm-hmm. Mm-hmm. Okay.
But just to add what Bernd was just saying, with these newer tools, when you're doing interpretation, look at as much of the data as you can, because you will see different things on the different frequencies, on the phase or real images and the imaginary or phase images. You'll get more out of it by looking at as much of the data as you possibly can. Mm-hmm. All right, well, we've got Eric here. Are there any questions on MUD and what we've been seeing?
Yeah, I have a question.
Yep, Roland.
Yeah. Would you provide a set of publications on the new tools, if possible, so we can tell what's the difference? The other question is there a repository of data for mud cake in oil-based mud? We have a lot of data available on oil-based mud cake. We have a lot of data available on oil-based mud, but oil-based mud cake itself is very poorly documented in the literature. If you are aware of a set of data, it would be helpful. Otherwise, we will have to open a kitchen and start making mud cakes and measuring all that good things. You know, I've heard everything from oil-based mud cakes are extremely conductive to oil-based, going back to Claude Boieldieu's days, if you remember, to oil-based mud cakes are just a sheer isolation. So if you are aware of anything, it would be helpful to share with us.
Right. Let me jump in and manage some of these questions that are coming through. Britta's got a hand up. Do you want to speak, please?
Yeah, thank you. Very interesting talk. I just have a question about the desiccation cracks. Is that because you get them geologically? Is that just the borehole environment? The speaker was cutting in and out. Is it like happening between the wall of the borehole, or is it a geologic feature?
It's
Can you
it's
re-explain?
happening. It happens on the borehole wall from the
Yeah. Okay.
from the phase change in the mud. So yes, it cracks on the wall.
Thank you.
In the chat, Islam Mitwali's been prolific. One question was, what was the logging speed when logging the imager with closed pads? Any ideas?
I think I remember it was around 900 foot per hour, which is half the speed, or even faster. I can't remember. But it wasn't outrageous. So
I'll generalize this next question to say, under what sort of conditions would you expect to be able to run a water-based mud tool in an oil-based well?
Oh, that the logging companies can for sure tell that. They have all their specs on their tools. I'm pretty sure that's out of my league.
Peter Barrett's in there.
Yeah, well, they work best, like we said earlier, really in higher resistivities. They don't work as well as the oil-based mud tools designed for oil-based mud, but in higher resistivities, as the example here or the other example from Bernd showed, they can actually generate a usable image, a more than usable image, a good image, but it's still not as good as those as from the tools that are designed to work in oil-based mud. So what we see here in this example from Bernd, the second track here, which is a water-based mud tool, the image is very good indeed, and it's certainly very interpretable, but we may be missing some of the fractures, for example, that we're seeing in the oil-based mud image next to it, or one of them may be slightly clearer, as we see round about, I think, 6.5 or so.
Yes.
So
This guy.
yeah. So they do work, but there are some compromises because they're not designed to work in the oil-based mud environment. So we'd rather be running the tools which are designed for oil-based mud.
No, obviously makes sense.